How well do you really understand private keys, public keys, wallets, etc.? In today's video, we are going to deep dive into how it all actually works. Let's jump in. Welcome back to another video. My name is Ian Major. I'm an entrepreneur, Bitcoin pleb, and all-around raging capitalist. And yes, we're going to nerd out a bit in today's video. I think it's fascinating, and I think it's really important to understand how this works. And the practical reason why I'm going through this slightly more academic topic is ultimately to build conviction. You know, the better we understand something, the more conviction we have. The more conviction we have, the more we can be dead inside when inevitably there is volatility, either in the fiat exchange rate for Bitcoin. This is all to arm you with a stronger foundation of understanding to build your conviction and capability and comfort as a Bitcoin user. For those returning to the channel, welcome back, my friends. As always, it is nothing short of an absolute pleasure to have you back. And for those new to the channel, and I know there are many of you watching, about 80% of you currently watching right this very moment are not subscribed. And so if you like this content, I invite you to consider subscribing and join us in our merry gang in cyberspace. I cover all manner of Bitcoin related content, including some of the sort of how it works, such as this video, but also wallet tutorials, running a node, Bitcoin mining, news, analysis, you name it, I cover it. But with all that out of the way, let's first start with just a very brief, high-level recap, and then we'll get into the meat of things. So I'm ultimately going to go pretty deep in this video, but first I just wanted to recap some kind of basic, more intuitive understanding of some of these concepts. And I've actually made a video on how the overall Bitcoin system works, which you can check out. I will link it in the description down below. So if you're rather new to Bitcoin, I would encourage you to probably start there. I'm going to recap some of those concepts right now for a few minutes, and then we'll get into the gory meat of today. But really, when we think about public-private keys, think of a private key really as nothing more than a very large random number. That would be unbelievably difficult to sort of guess. And we'll get into just how difficult that is later on in the video. But the private key ultimately controls your funds because you need a valid private key in order to send the your Bitcoin, right? So think of it in some crude way like a password or PIN to your bank account. Now, the public key is derived from the private key, and you can think of this crudely akin to your sort of bank account number itself, right? If I want to send funds to an individual, but even then it's not perfect because you also have what are called addresses, right? And addresses are derived from the public key and basically serves almost as a pay to the order of X, like if you imagine an old school sort of check, right? So the address kind of is an abstraction, one step abstraction away from a public key that ultimately allows you to send funds to a particular destination within the network. So private key, really just a big random number. Public key is derived from the private key. Addresses are derived from the public key. And we can see that nicely sort of summarized in this image from the Mastering Bitcoin book that I will link, which is again freely readable. So again, I'm gonna use a number of kind of resources as we go throughout this this video, all of which I will link in the description down below so you can check them out. And we'll talk about these sort of methods. But basically, the basic idea is public key derived from private key in a way that you cannot reverse engineer. So you can't take a given public key and reverse engineer the private key that it came from. And similarly with the with Bitcoin addresses. And so a wallet is really just a data file that contains your key pairs. And indeed, there are multiple, as we will discuss. Most modern Bitcoin wallets are what are called deterministic. So hierarchical deterministic wallets, or HD wallets. You've probably seen this in different Bitcoin wallet software. And if you've ever wondered what that means, that's what it means. And it's basically this idea that from a given seed, we can actually derive many pairs of private and public keys. So that's very high level. Let's now jump in and understand that entire sort of derivation start to finish. All right, so let's get into the fun stuff. So step one in this entire process, as I alluded to just earlier, is the creation of what is essentially a very long random number. And the way that a computer will generate this in whatever kind of wallet software you're using is initially in binary form. So literally, anywhere between 128 bit to a 256-bit string of zeros and ones. And so an example of that is what you can see here, like literally a gigantic string of zeros and ones. Now, your wallet software is going to have some random, kind of number generator built into it and the operating system. But there are also many software providers that allow the addition of user-generated entropy, entropy being akin to randomness. So that means you could literally do like dice rolls. And, if it's a 1, 2, or 3, it's a 0. If it's a 3, 4, 5, 6, it's a 1, right? So you can use dice rolls to generate your own entropy and randomness if for whatever reason you don't trust the randomness of the whatever it is that you're using, whatever wallet software you're using to do this. And so again, this is for the most part, if you're just kind of going into any modern wallet software and you're clicking to generate your recovery phrase, so the mnemonic phrase, which we will get to, all of these initial steps are happening kind of behind the scenes. So this is step one. We have this big long string of zeros and ones, anywhere between 128 of them to 256 of them. And the length of that will ultimately correspond to the number of words in our mnemonic phrase. So this is the recovery phrase that we are, most of you have seen, that allows you to essentially back up and recover your wallet if something were to ever happen. So 128 bits will correspond to 12 words in your mnemonic phrase, whereas 256 bits is going to correspond to 24 words. And those are the most common, but in fact there are, you could do between that as well. So in this example initially, I'm going to use a 12-word sort of phrase, and therefore I've got this 128-bit string of zeros and ones. Now the next step here is that your computer is going to break this long string of zeros and ones into 11-bit chunks. Now, if you've got your kind of critical thinking cap on, you may say, well, Ian, if it's 11-bit, like 11 is a weird number, right? If I take 128, which is the total number of bits that we're working with, and divided that by 11, I get 11 groupings, but I only get a partial grouping for my very last one. And so each of these 11-bit groupings are ultimately going to map to a word in your recovery phrase. And so how do we get that final 12th word? How do we sort of complete that, given that we only have partial, a portion of that final 11-bit grouping? And the way we do that is by creating what's called a checksum. And so what happens is sort of the entire string, in its entirety, is run through SHA-256. SHA-256 is a cryptographic hash function, which basically takes some variable length input and produces a fixed length output. And so there's it's sort of random in the sense that like you can't figure out its logic. Like if 0.0000001 produces a certain output, and you think, okay, so therefore 0.0000011 is going to produce this other output logically, that's not the case. It could potentially create something completely different. And so what happens when you run the string through SHA-256 is you ultimately end up with something like the following. So this is a hexadecimal SHA-256 encoded string. And to get the checksum, what happens is, in the case of a 12-word recovery phrase, you're going to take the first digit, or the first character, rather, the first item, so that in this case an F, and map that to binary. Perhaps even more foundational concept is that there are a variety of ways to encode information or data, right? The most foundational level is bits, zeros and ones, but there are a variety of other formats, including, hexadecimal, which basically includes, 0 to 9, as well as I believe it's A to F, right? And so you have a lot of different combinations that you can create with that. And then you have like decimal format, which are just, going to look like regular numbers, et cetera, et cetera. And so you can take an F and map that back to binary. So that F might be, whatever, 0100. I don't know what it actually is. And so that's how you complete the final part of that 12th grouping in the case of our example. And the reason for all of that is so that you can kind of validate that the mnemonic phrase is valid. And so in our little example, what we now have are these nice 12 groupings of these 11 bits each. And we can map that to a decimal representation of each of these groupings. And so, for example, in that first one, 11111011000 maps to 2008 in decimal form. And so you can kind of see where this is going. We're from mapping each of these binary groupings into its decimal form. We then take that decimal form, and there is literally a lookup table. No joke. There is literally a lookup table for each of these decimal numbers and the word that they map to. And so there are actually a number of different languages supported by wordless. This was codified as part of BIP, or Bitcoin Improvement Proposal 39. And so I'll link this in case you're curious to check it out. But there's a number of kind of languages supported here. The English lookup table is literally this, like number 1, if you were to get a 1, is literally abandoned. Number 9 is absurd, and so on and so on and so forth. And so there's 2,048 total possible words in each of these lists. And so coming back to our example, we can now match up the words that are associated with each of those decimal representations. And there we go. We've got our 12 word recovery phrase. So pretty cool stuff. Everything from here is now deterministic. We're going to use this phrase to derive everything else, our private keys, public keys, addresses, etc. So let's move on now and see what happens next. All right, so now that we've got our 12-word sort of recovery phrase that, again, was just derived from this original really long random series of zeros and ones, we can now proceed with the next step, which is to create a cede. And the root cede is basically from which everything else is derived. And so as you can see in this visual, the way this is derived is through something called the password-based key derivation function 2, or PBKDF2. And essentially, this function takes a couple of inputs. Number 1 is what's called a password. The password here in this case is nothing more than the mnemonic itself. So that is literally being passed into this function. And then you also have another input, which is the salt. And so the salt is going to be the mnemonic phrase plus an optional passphrase. So whenever you've seen the word passphrase in some of these wallet softwares that you've used, you'll know that number 1, it's optional, but number 2, maybe you've wondered like, well, how does this sort of fit into my overall kind of security? And what it's really doing is it's adding some additional entropy to this salt item that goes into this function. And so you now have the mnemonic phrase and the mnemonic phrase plus the optional passphrase. And so all of that is passed through the PBKDF2 function. And the result is a hexadecimal seed, which could look like the following in our example. So now from this seed, which again we derived all the way from that original sort of long random list of binary, we can now basically spin up everything else that we need in our wallet. A great way to visualize this is the following. So we've got our root seed here on the left that we just talked to, and this is of course associated with our mnemonic phrase. And now we can pass that through a one-way hash function, which is this sort of composite HMAC SHA-512, which will result in a 512-bit output. Now, the first half of that output is what's called the master private key. Again, we're talking about the sort of hierarchical deterministic wallet structure here. The right side of that 512-bit output is what's called the master chain code. And this is really what's going to add additional entropy in order to allow for the creation of many different private public key pairs. So the master in master private key implies that it's sort of able to create, children keys, and those children keys are able to create additional keys, et cetera, et cetera. And so in fact, there can be many different private keys associated with your wallet. And so it ultimately results in this sort of tree, right? You've got this ultimate seed, and that's why you interchangeably hear the terms seed phrase or recovery phrase or mnemonic phrase. Ultimately, they all might not be like precisely identical in terms of their encoding, but they all represent this sort of seed, right? From which you derive the master private key. That private key is what derives the public key, and so on and so on and so forth. And each of those key pairs can also create additional kind of children keys as well. And so this basically just gives a lot of flexibility to a given wallet. All right, let's take a quick breath and recap. So again, we started with this really long binary number. We chunked that up, created a little checksum, and ultimately derived our seed phrase or our recovery phrase. We created the kind of hexadecimal representation of that, and then used that to create our master private key and the ability to create additional key pairs as well. So we've sort of gotten from the very start up to our private key. Let's now talk about how public keys are generated from said private keys. And so a public key is derived from a particular private key using elliptic curve digital signature algorithms, or ECDSA. And as you can see in this visual, the particular kind of elliptic curve used in Bitcoin's case is SECP256. Right, this goes kind of well beyond my knowledge and understanding in terms of the actual elliptic curve math, but it's actually not as intense as you might think. But I will link a couple of resources in case you really want to dig into the actual math. But essentially, conceptually, what's happening is that there's a constant g, so there's this kind of predefined point g. And by passing the private key in, you can generate a public key on this sort of coordinate system. And this math works in a one-way fashion. So, it's not the case that you can take a public key and reverse engineer the private key. Now, it's important to be aware that this digital signature method is actually being upgraded as part of the Taproot upgrades that you have probably heard a lot about. I've actually made a whole video on this in terms of what it will do, what it won't do. And so I'd encourage you to check that out because there's definitely some relevance here in the form of the Schnorr digital signatures that represent an upgrade from the current elliptic curve method that I've just described. And so Schnorr signatures will have a number of benefits, again, that I explain more in that video. So I encourage you to check that out. But that is definitely an exciting development. Taproot at this point, having been fully kind of passed earlier this year, is set to be activated in November. So exciting stuff right around the corner. And so we've got one more step. So we've got our public key derived. Now, how do we actually get to the Bitcoin address that you'll paste in, or you might have a QR code that represents that sort of address string in order to kind of send and receive funds. And so the way that works is the following. The public key is basically double hashed. So SHA-256 is first applied to the public key, and then the resulting output is passed through another hash function called ripemd160. And so you ultimately come up with this hash, this sort of double hash, if you will, of the public key. And then there's what's called this base 58 check encoding that essentially makes it a little more readable for a human. So a lot of hashing, a lot of cryptographic hash functions being used here, but hopefully this at least enlightens and sheds some light on this process, right? All the sort of steps that are happening behind the scenes when you click a button to generate your seed phrase. There's actually an awful lot happening, and every time you subsequently create an address, there's also a lot happening behind the scenes as well in terms of the derivation from your public key as well as the private key. And how all of this comes together in sort of real time to sign messages and signatures, etc. So with that understanding, I want to conclude with some practical implications of everything we just discussed. And specifically, I want to focus on this question of how hard is it to crack, Bitcoin? Let's discuss. And so that question I just posed is actually a little bit malformed and not quite right. When people say crack Bitcoin or crack SHA-256, SHA-256 is a cryptographic hash function. And so really what I think people mean when they ask that question is how hard is it, or how long would it take to create a collision, right? To create the same sort of output that's kind of already been generated using a given input. How hard is it to create a collision is essentially what, or perhaps a more accurate way to frame that question. Let's start with just a starting point, which is that the size of Bitcoin's key space, so basically 2 to the 256 power, right? You have 0 or 1, can be 0 or 1, so that's the 2. And then you have 256 of those things. In the case of a 24 word seed. And this is just an impossibly large number. You can't even, the human brain cannot even wrap its mind around how big of a number this is. If we translated that into decimal form, it would be about 10 to the 77th power. And it's estimated that there are probably about 10 to the 80 atoms in the observable universe. Okay, let that sink in. 10 to the 77 possibilities, 10 to the 80 atoms in the universe. But that doesn't give us the full picture, right? Because computation, as we know, has rapidly progressed. The power of these ASIC miners in terms of doing these, cranking out these hashes is getting better and better and better. And so how long would it take to brute force that? If I wanted to find a particular private key so I could essentially steal someone's funds, how long would that take for me to actually crank through, given that we have incredibly powerful computation today? I like this particular answer. It is a bit dated, and so the actual answer here has probably changed, or it has certainly changed, given that the hash power has grown quite a bit since this. But so what this says, let me show you some calculations meant for calculating time taken for finding a collision in the hash function. So SHA-256 is 256 bit, and I have assumed what's something called the birthday paradox, which essentially cuts that down to 2 to the 128 attempts. So you'll need 2 to the 128 attempts. Taking all the hash power at the time this was written. This was back in 2018. So again, this has grown significantly since then. But as you'll see, that doesn't make any difference whatsoever. You basically can calculate the number of attempts that you can conduct per second. So as he says, or as this person says, if all miners of the world, all mining pools combine and try to find one collision, just one, in SHA-256, you ultimately need 2 to the 128 divided by, blah, 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 seconds, which equals, 5 times 10 to the 18 seconds, or approximately 174 billion years, while we know the age of the universe is nowhere even remotely close to that. And that's just to find one collision. So again, this is an absolutely extraordinarily large number that has absolutely just like zero chance, like zero probability of being able to generate a collision. But I know some of you listening are saying, but Ian, what about all this FUD I periodically hear about quantum computing and how quantum computing is going to surely break this? Let's look at another potential constraint on how this would work. And that constraint are the very laws of thermodynamics themselves. And thus far, we have not found out any way to violate those laws of physics. And so I'm just going to read you this entire thing because I think it is absolutely fascinating. So imagine you built a perfect computer. Forget about, gigahash, megahertz, blah, blah. You build a computer which uses the absolute minimum amount of energy theoretically possible to record a change in a single bit, i.e. 1 to 0 or 0 to 1. We are talking about the limits of thermodynamics. Nothing more efficient is even possible. Now imagine, right? So we're nowhere close to that. Now imagine that you used most of the natural resources in our star system to construct a Dyson sphere and covered the entire surface of this sphere with a single star system sized supercomputer. Okay, so you took all the things in our solar system, built a Dyson sphere that can perfectly extract energy from all these different resources. And we built this absolutely astronomically gigantic supercomputer. And now imagine you could keep this supercomputer somehow cooled at roughly absolute zero and could do this without expending any additional energy, which is, I don't know how that would be possible. If you had that and captured with absolutely no inefficiency or loss the entire energy output of our star, not just in a day or week, but continually until it burned out, you couldn't even count to 2 to the 256 before you ran out of energy. That's just counting. That's not even hashing, not even comparing or performing lookups, just counting from 1 to 2 to the 256 minus 1. And so you would literally run out of the energy in our solar system before you were able to even count to, count up to this number. Perhaps we become a, level 3 civilization, level 1, 2, 3, I forget the different Kardashev scale tiers, but, perhaps we one day harness the energy in not just our solar system, but the entire galaxy. And, this could slowly start to change, but it still gives you just this absolutely absurd kind of challenge. And so importantly, these numbers have nothing to do, it says, with the technology of the devices. They are the maximums that thermodynamics will allow. And they strongly imply that brute force attacks against 256-bit keys will be infeasible until computers are built from something other than matter and occupy something other than space. Bitcoin, your money is secured by the laws of the universe. So that, I think, is honestly the most interesting, right? Like, even if we had quantum computing, whatever that means, and I think people just sort of like blindly throw that out, there's probably like a dozen people on this planet that actually understand quantum computing and are at the forefront of that in such a way that they could intelligently comment on its potential to find collisions in SHA-256. But like, even if that ultimately happens, how could it really could it really break it in a reasonable amount of time, given the energy requirements that would presumably be required in order to do that, even with, a much more kind of efficient machine? Remains to be seen. I think the other piece that we obviously know is that as quantum technology advances, inevitably there will be quantum resistant encryption that can be embedded within the system. And so that's the beautiful part about the fact that, Bitcoin is programmable. It's not designed to change very fast, and that is a good thing. That's what you want for your base level monetary system. But it is programmable and it can change. And so that is some food for thought that I invite you to consider. Let's go ahead now and wrap this video up. All right, my friends, so today we took quite the trip down the rabbit hole around private key, public key, addresses, and all the sort of derivation that happens and how all of that is created within a particular Bitcoin wallet. And we also looked at the practical implications of that, not just from the perspective of how long would it take to brute force find a collision with a hash for the SHA-256 algorithm, but we also looked at this angle around thermodynamics and the fact that we wouldn't even have enough energy in our entire solar system to power the counting of this sequence of numbers. And so with all of this, hopefully what I've done, my goal for this video was to you may have known a lot of these concepts really well. Maybe you knew these concepts not at all, but regardless of where you were on this spectrum, I hope this video gave you at least something more to deepen your knowledge and understanding of these really important concepts, and give you conviction that this is as secure as it gets. Like, you can't get more secure than this. Anywhere, at least in our known kind of, Earth. So I hope you found this valuable and useful. If you did, you already know what to do. Give this video a like. Leave your thoughts and comments down below. I'm curious to hear what you think of this. And not just this, but also other potential videos that you'd like to see in the future. I really do take that into account when making the schedule for the channel. But for now, I'll let you digest all this cosmic Bitcoin truth, and we'll go ahead and leave this video here. As always, my friends, every sat counts, especially when it's protected by the thermodynamic laws of the universe. And until next time, I'll see you then.